we're going to do just a couple quick mole problems. Then we're going to talk about proportions, whatever. And then we're going to talk about the concept of chemical analysis. We're all familiar with proportions, basically the ratio of one thing to another. Here we're going to apply that to all mixtures, compounds. We've been talking about mole ratio. That's just a simple proportion as well. Remember that after we finish today, you will be able to easily go through all the tutorials for Chapter 4. All you need to do is the first 4. Those allow you to send an email. Once you've sent the email from each of them, go to Blackboard, click on the link, and say yes. And you get 5 points. Isn't that easy?
How many we have to do? Like how many tutorial we have to do? Like do you need to do at least 3 or more?
First 4 tutorials.
First 4.
And so not the quiz, just the first 4. This is intro, not info. At Chemistry Online, that's the one that comes up automatically. This will stay up until Friday. So you have plenty of time to get your 5 points. Also remember the makeup exam, second chance, also goes off at 11:30 on Friday. All right, we were talking about the mole and our friend Avogadro. Remember, it has 6.02 times 10 to the 23rd things. The mass of 1 mole, the formula mass in grams, is called the molar mass. We talked about the concept of molecular weight. All you do is add up masses. For instance, for something like glycine, it looks like this. 75.07 atomic mass units. Express that in grams, and we get the molar mass. Neat thing about moles, we said, was you can take the molar mass of any chemical substance and know that it will contain the same numbers of particles. That's going to be very important if we're trying to react A with B. 1 mole of oxygen, 32 grams. Mole of calcium carbonate's 100 grams. Simply formula mass expressed in grams. This was an exam problem. We have carbon tetrabromide. It weighs 331.6 grams per mole. You are given that you have 8 times 10 to the 22nd molecules. Quickly calculate how many grams of this stuff you have. While your mind is going a mile a minute right now, you're thinking, I need to convert my number of molecules into number of moles. If I know how many moles I have, and I know how much 1 mole weighs, then I know how many grams I have. All right. Start off with our given here. That's our number of molecules. We want to convert this to moles, so we're going to use Avogadro's number of molecules per mole. Molecules has to be in our denominator so that these will cancel. Next, once we have number of moles, we want to convert that to grams. If we know the number of moles, and we know what 1 mole weighs, 331, then we can simply write this. Molecules will cancel, moles will cancel, and we get grams. Once again, run through the math on your calculator. Make sure you can do these big ugly numbers. And you should get about 46 grams of carbon tetrabromide. All right. What we're going to do is take our mole ratio concept and allow us to use this to calculate the percentage of a given element in a compound. Okay, now this is going to be simple, it's going to be important. We know that if we write a mole ratio for hydrogen and HCl, we look at HCl. How many moles of hydrogen in every mole of HCl? Well, it's 1, right? Okay. Now, we know that 1 mole of hydrogen weighs what? Look at your periodic table. Weighs a gram, right? So 1 gram of hydrogen is the same as 1 mole of hydrogen. How about 1 mole of HCl? If you add it up, it's about 35.5 grams. So instead of saying 1 mole of hydrogen, 1 mole of HCl, I could say 1 gram of hydrogen, 35 grams of HCl. I've converted my mole ratio into what I'll call a mass ratio. All right, now say I wanted to say, if I know my mass ratio, what's the percentage here? All I have to do is do the division, multiply by 100. There is 2.84% of hydrogen by mass in HCl. Most of the mass, 98% or so, is fluorine, and about 2.5 or 2.8% is the hydrogen. Now that's really simple, isn't it? We take our mole ratio, convert it to a mass ratio, do the math, multiply by 100, and we get percent. We have calcium fluoride. What's the percentage of fluorine in calcium fluoride? In order to do this, you need to look at your periodic table. We'll see that fluorine is 19 grams per mole. We add up, calcium fluoride is 78.08 grams per mole. All right. We're going to set up a mole ratio. How many fluorines in every calcium fluoride? Well, there's 2, right? There's 2. And each one weighs 19. So we start off with our mole ratio. 2 fluorines in every calcium fluoride. Each fluorine weighs 19 grams, doesn't it? And calcium fluoride weighs 78. So we multiply this out, get 38 divided by 78. That will give us our percentage on it. Roughly 48 point something percent. Now this is simple. We can all do this, right? Right. We can do this. What is this stuff?
9 oxygen.
Sc is what element? Scandium. ClO3 is what?
Chlorine.
8.
One of the other.
And what's the oxidation number? Fluoride is a -1, isn't it? And there are 3 of them. That means our scandium
Is +3.
must be +3. All right, so scandium 3 chloride, 295.3 grams per mole. We want the percentage of oxygen. We start by doing our mole ratio. Convert that to a mass ratio. Do the math and get our percentage. I want to make sure everybody can do this. What's the mole ratio of oxygen to scandium 3 chloride?
3 to 1.
Is it 3?
This is 9.
9. 3 times 3. 9 oxygens per scandium 3 chloride. So every oxygen weighs 16. 9 times 16, and 295 on our bottom.
For the bottom number, are we adding all those mass, like
Yep, add everything up.
adding and multiplying and all the other stuff? Is that how we get that big number?
That's how you get the bottom, the molecular weight. All right, we do our simple math here. 9 times 16 divided by 295. This is 48.8%. All right, so we can do a mass ratio pretty easy, can't we? What's the mass of fluorine in 1 pound of magnesium fluoride? That's 454 grams. Well, you see, this is a twist on the thing. Here, we're going to have to figure out basically the percentage of fluorine in magnesium fluoride. So we're going to set up our mole ratio, convert it to a mass ratio. We could calculate the percentage there, right? So, fluorine is 19. Magnesium fluoride is 62.3 grams per mole. Our given here is going to be our pound of magnesium fluoride, but we'll use that in a moment. First, go ahead and set up your your mole ratio. Mole ratio is just going to be 2 to 1. Every fluoride is going to weigh 19. The whole thing weighs, I forgot, 62. So we have 38 divided by 62. That would give us our percentage. But we don't have to do that, do we? Because what's our given here? The given is grams of magnesium fluoride. What's our denominator here? Grams of magnesium fluoride. All I have to do is take my given and multiply by this by my ratio. Here's my given. I'll just take this whole thing, move it down for my ratio. This will cancel, so I only need to calculate once. 454 times 2 times 19 divided by 62 gives me 276. it should be 3 significant figures. Whoops, so that's wrong. It should be 277 because we have 454. See, here we made our mass ratio, and then we use this as the ratio in our algorithm. We were trying to use this as a given. Here it is. We could have flipped it upside down if it was the other one, couldn't we? Let's show that. This is sulfuric acid. Sulfate, we all know. 1 sulfur, 4 oxygens. In sulfuric acid, H2SO4, everybody's favorite acid, all you do is put a hydrogen on 2 of the oxygens. We'll talk about that more in chapter 8. All right, we have 5 grams, or we want to know how much sulfuric acid we need to have 5 grams of hydrogen. Now that might sound like a funny question, but let's figure out how we're going to do that. Hydrogen is 1, sulfuric acid is 98. Our given here is grams of sulfuric acid. So what I'm going to do is set up a mass ratio for hydrogen to sulfuric acid. I'm going to put that mass ratio with grams of sulfuric acid in the denominator, and then just multiply it all out. Let's see how we do this. There are 2 moles of hydrogen in every sulfuric acid. Everybody's happy with that. The mass ratio would be 2 over 98. Now our given here is grams of hydrogen, right? Grams of hydrogen is in our numerator. So we're going to have to just flip this upside down. But we can do that. Here's our given. I'm going to take this ratio, flip it over. So grams of hydrogen cancel. And I get grams of sulfuric acid. Once you play with this method enough, given and ratios and stuff, you'll really appreciate just how easy this makes it. Just remember, units of given in your denominator. So what's the answer? 243.3 grams of sulfuric acid. We're at 3 significant figures. Should be, 243.
This is the mole and mass relationship tutorial.
Well, let's come, no.
We covered that.
We
That's why I'm
covered that
confused. So which tutorial
What's
is
coming
this?
up now? Well, this is another mole mass. You see, each of these tutorials is designed to ask you a number of different types of questions, believe it or not. It sits there, does a random number, decides which question it wants to ask you. And then it takes and plugs the numbers in. So there are 3 or 4 ways that each of these can answer. Let's say we have phosphor, what is this? What's PO3? That's phosphate is PO4, phosphite is PO3. We'll see in chapter 3 this is phosphorus acid. And it contains 0.555 moles of hydrogen. How many grams of this stuff is present? All right, to do this, we need to do a mole ratio. Moles of phosphorus acid, moles of hydrogen. Moles of hydrogens are given, so it's in the denominator. We're 1 to 3. we're looking for grams. We are given moles of hydrogen, multiply moles of hydrogen by our ratio, we get moles of phosphorus acid. We've done that. Finally, if we know how many moles of phosphorus acid we have, and we know each one is 82 grams, this is 15.2 grams in our sample. Any questions? All right, let's take the notion of the mole ratio that we've used here, and let's apply it to the next tutorial, and that is the percentage composition. Now, as a warning on this one, you would think that these are going to add up to 100. So it would seem logical that you could do 2 of them, subtract from 100, and get the last one. Doesn't work that way. Rounding is such a bear that this always comes out either 99.5 or 101 or something like that. So go ahead and work it for each of them. But in this tutorial, all we have to do is figure out the mass percent for each of these guys in our compound. Now this isn't tough. We know our mole ratio of nickel in this is 1 to 1, right? We know that nickel is going to weigh 58.69, and the whole thing is going to weigh 161.6. Therefore, our mass ratio is simply this, multiplied by 100, we're at 36%. Quickly do chlorine. How many chlorines are there? 2. By the way, what is this called? What is OCl? Not OCD. OCl, hypochlorite. What's the charge on our nickel? Every hypochlorite is -1. This must be nickel 2 hypochlorite. All right, so we have 2 chlorines. They each weigh 35. Divide by 161, 43.9%. Oxygen. We have 2 oxygens. Each of them weighs 16. Divide by 161, 19.8%. What is this? ClO2. Gonna be a chlor something, isn't it? Chlor something. Chlorate is the parent. So this is chlorite. Calcium, do we need to show an oxidation number? No, because it's group 2. It's always going to be +2. Calcium chloride. There's 1 calcium per. 40 grams each, 175 our total. Percentage of calcium, 22.9. How many chlorines are there?
4. No, 2.
2 chlorines. So it's going to be 2 times 35.45 divided by 175. or 40.5%. And finally, how many oxygens?
4.
4 of them at 16 each, or 36.6%. Once you do a bunch of these, or a few of these, do your 5, you'll see this really can be simple. Very nice practice in doing mole ratios, then just converting that to a percentage. All right, almost through here. Let's just take a break and let's look at something cute like molecular models. We've used these throughout the course. Let's just get familiar with them again. We actually made ball and stick models in lab. They're like little tinker toys. Space filling model, you take the atoms, you do a calculation. You calculate what's called the van der Waals radius. That's how far the electrons actually extend from the nucleus. And you draw a surface. Now this really looks like the molecule, and it's cute. This shows you nicely where the bonds are. So this is more useful, but this is much cuter. Our color scheme, universally, almost universally. Carbon will be black or gray. Hydrogen, white or gray. Oxygen's almost always red. Nitrogen's almost always blue. The other guys, you kind of try to pick out what the element looks like. So sulfur is yellow, for example. Iodine will be purple. Chlorine will be greenish yellow. Bromine will be brown. Whatever. Remember, there are a number of diatomic elements we must remember. All the halogens. Then oxygen, nitrogen, and hydrogen. This is space filling for bromine. It's brown. It's Br2. And again, it's just 2 balls stuck together. Now we talked about molecular formulas. There are simple ways to reflect the molecular formula. The simplest is just to look at your molecule and convert that into atoms. If we look at this guy, we have 2 carbons. We have 1, 2, 3, 4, 5 hydrogens. We have 1 nitrogen, and we have 2 oxygens. So the simplest way to write our molecular formula would be to just do C2, H5, N, O2. Simply string out the elements. But as easy as that is, this is almost useless. If I give you this and say, what is it? You'd have no clue. So this is useful, nice and concise. It's a condensed formula, but it tells you nothing about the structure. You'll also see these things written out so that they're strung together to tell you more about what the molecule looks like. We could say that we have a nitrogen with 2 hydrogens, and that's bonded to a carbon with 2 hydrogens. And that's bonded to a carbon that's bonded to 2 oxygens, and one of them is an OH. So this tells you more about the structure. We'll kind of use things like this a bit because they are more informational. You could go a little bit further. We could say we have an NH2 here, and that's bonded to a CH2. That's bonded to a carbon with a double bond to an oxygen, which is bonded also to an OH. So this is often called a Kekulé formulation. This is very, very useful because it tells you exactly how things are put together. It's also a pain to draw. So quite often you'll see just a compromise between one structural representation and the other. Just get used to seeing them and interpret them this way. Now, that's what a molecular formula is. It tells you what the molecule is, the ratio of the atoms, etc. There's another type of formula, and that's called the empirical formula. The empirical formula is different because what you do is you take the molecular formula for glucose, C6H12O6, and you rewrite it as the lowest whole number ratio of the elements. So if we have 6 carbons, 12 hydrogens, 6 oxygens, what's our ratio? 1 carbon, 2 hydrogens, 1 oxygen. The empirical formula is CH2O. Now, this is acetic acid. This is the acidic component of vinegar. I've written the structure this way to show it's a CH3 and then our COOH. But the empirical formula here is exactly the same as that for glucose. So you might say, why in the world bother with empirical formulas? They don't tell you much about the molecule. As we'll see in a second, the reason we want to do this is that when you do an analysis, try to figure out what something is. What you get is the empirical formula. Then the challenge of being a chemist is to convert that into the structure. Look at these guys and quickly just jot down their empirical formula. Acetylene. This is the stuff you burn in torches if you want to do big time welding. 2 carbons, 2 hydrogens. What's the lowest whole number ratio? CH. Benzene, C6H6. This is acetylene. This is a carbon-carbon triple bond. Benzene, we've seen it before. It's a ring, 6 carbons, 6 hydrogens. Our empirical formula is still CH. What's the empirical formula for water? H2O. That is the lowest number, right? The lowest whole number ratio. But peroxide, the fizzy stuff you put on cuts that doesn't really help, is HO. All right, what we're going to do here is simply talk about empirical formulas and chemical analysis. Now, this isn't going to be on the exam. All right, you're not going to have to do this type of problem past this one here. But I want to show you why we care about empirical formulas. If I tell you my mole ratio for carbon to hydrogen in a compound is 1 carbon, 1.33 moles of hydrogen, what is my true empirical formula? Remember, it must be whole numbers. Well, what we have to do here is to simply take CH 1.33 and fiddle with that until we get whole numbers. How can we do that? If we multiply both of these by 3, what do we get? We get C3H4. When we do analysis, we wind up with a number like this, 1 to 1.33, and then we have to figure out the empirical formula from that. Analysis looks like this. Let's say we have a hydrocarbon, so just carbon and hydrogen. We take a little bit of it, put it in a tube, and heat it up. We pass oxygen over it. What this does is it converts all of the carbon to CO2 and all the hydrogen to water. Now, the stuff that comes out then passes through phosphorus 5 oxide. You could all write that structure, right? Where the water is absorbed. It then passes through here, sodium hydroxide, where the CO2 is absorbed. So what you do is you weigh these guys before, you weigh them after, and you see what mass of CO2 you get and what mass of water you get. For example, if we have 0.115 grams of unknown and we get 0.379 grams of CO2, 0.1 grams of water, what is our empirical formula? To get moles of CO2, how would you convert grams of CO2 to moles? You know that every mole of CO2 weighs 44 grams, because you add it up. So, 0.379 grams of CO2, 44 grams per mole. CO2 cancels. We have 8 times 10 to the minus 3 moles of CO2. Now there's 1 carbon in every CO2. That's our mole ratio. All of the carbon came from our unknown. So we know we have 8.6 times 10 to the minus 3 moles of carbon in our unknown. For water, we got 0.1 grams. It weighs 18 grams per mole. So we have 5.7 times 10 to the minus 3 moles of water. Here, our mole ratio is 2, though. So all the hydrogen came from the hydrocarbons. So how many moles of hydrogen? We just have to double it. So now we know how many moles of carbon we have, how many moles of hydrogen.
You double hydrogen?
Yeah, because there are 2 hydrogens in every water. So this is our mole ratio. Now, this is a little ugly looking. There's a real simple trick to convert something like this into happier numbers. And that is to look at them and say, which is the smallest of the 2? Which is smallest? Our numerator, right? What I'm going to do is divide both numerator and denominator by the smallest. When I do that, my numerator now becomes 1. And my denominator becomes 1.33. So what's my empirical formula? C3H4. This is how you would do an analysis. Now when I wrote this problem, I actually wrote it for 1,3-cyclohexadiene. 6-membered ring, 2 double bonds, looks like this. Ball and stick, it would look like that. See the double bonds here, and this is space filling. However, because this is just an empirical formula, the analysis also fits all of these guys. And if you decide to make it to organic chemistry, you'll see that one of the great joys in life is trying to figure out which of these guys it really is.
That's good.
Any questions? All right, finally, let's end up with proportions. We've been doing proportions all day. Proportions are simply the ratio of two numbers. Now, we'll do this a lot in the gas laws and stuff like that, chapter 9. But if we have two variables, x and y, we can always make them equal by sticking in a constant. Constant, if we pull it out, is simply the ratio of x over y. Now we've done this. Density is simply mass divided by volume, isn't it? It's a ratio. What we're going to do is look at 3 examples of ratios and show how we can take that ratio and use it in our problem-solving algorithm. Again, this is not complicated. These are just examples that we can work with. Let's say we have a mixture. Somebody tells us there are 3.4 grams of impurity in every 200 grams of this stuff. Now in our little bucket here, we have 25 grams of our mixture. How much impurity? What we're going to do is simply use this, 3.4 over 200, as our ratio. And we'll use this as our given. We have 25 grams of mixture. We know there are 3.4 in every 200 of impurity. We set it up so that mixture is in our denominator. Mixture cancels. And we have 0.42 grams of impurity in our 25 gram sample. So we simply took this word problem, took these guys, and constructed a ratio based on those. Now the next one we've actually used before. If I tell you CO2 is 27% carbon, how can we express 27% as a ratio? 27 over 100, that's what it means. So here, we are given we have 255 grams of CO2. Here's our ratio. How much carbon? About 69 grams. And the last one is something that we've all seen a lot of, and that's parts per million, parts per billion. We know that if there are too many parts per billion of bacteria in the lake, we can't go swimming, right? What does that mean? Parts per million, parts per billion are simply ratios. 1 gram over 1 million grams. 1 bacteria over 1 million bacteria, etc. Well, this is sushi. Very good. We know that tuna is very good, but it can contain mercury. And mercury is not good for you. Makes you stupid. Okay? You're advised not to eat too much mercury-containing tuna. Well, you walk into your sushi restaurant, you see a sign says, our tuna has 988 parts per million of mercury. So you look and you say, well, that is a big number. It's only 988. I guess I'll eat some. Okay? So we sit down and we eat 100 grams of sushi. How much mercury did we just eat? And how stupid will we be? Sorry. Okay. parts per million, we're looking at 988 grams of mercury in every million grams of sushi. We are given 100 grams of sushi, sushi cancels, and we're left with 988 milligrams of mercury. This is enough to make you really, really sick. If you go into a Japanese restaurant and you see something like this, I would leave, okay? This is enough mercury to really do you in. All right, 3 simple examples of how we use ratios, plug them into our algorithm like this. These are just different types of the same types of ratios. All right, we'll stop here. And next Wednesday, we will